Hello guys, welcome back to the journey to relativity, this being the second part of that journey. And in essence, if you've seen the first video completely, you've noticed that there are some things which I haven't gone over. My initial intentions were to go over a little bit of the basics for vectors before finishing the video, but due to editing, I noticed that, I will keep it a little bit shorter, and I decided to cap it up to the scale factors and how you can calculate the metric of a coordinate system using scale factors. In this video, we are going to be diving a little bit more into vectors and trying to look at their different properties. And also we will look a little bit more closely to index notation and specify some things. So without further ado, let's delve into it. First things first is I want to make two notes in regards to the previous videos, and that is that the notation which we use, the Einstein summation, of say dxi times dxi, so dxi squared, that this implies a sum notation basically. But with the Einstein summation, you just drop this sum notation. This is only true given the fact that we have just two indices that are the same here. No more, no less. If you have two indices, then this implies indeed that there is a summation happening here. But if that's not the case, then there is no summation happening there, and it might just be something to the power of something or a particular transformations, such as we will see very briefly. And the second note which I wanted to make is the technique of using scale factors in order to find the metric is a technique that works only for orthogonal coordinate systems, but for non-orthogonal or skew coordinate systems, then you would have to do something slightly different if you want to find the metric. Now, with that out of the way, we can get into the content of vectors. Well, if most of you have already done a little bit of math, and I expect that you're a little bit familiar with it already, you know that a vector is a mathematical object which you can consider to have a magnitude and a direction. At least that's how it's typically taught in a lot of physics classes. And that is true, but mathematically speaking, you can think of it in a more abstract way of saying that a vector is an object that exists in Rn vector space, which is a little bit more jargony, but it is a more rigorous way of thinking about it, which if you want to know more a little bit about that, I encourage you to look up some YouTube videos on vector spaces and the spanning properties of vectors, basically. So if we have a vector, which we will denote in the typical classical physics sense of an arrow with a particular magnitude, then we can know different things about this arrow, which we will call vector v. Well, we know, for example, it has a magnitude, and we also know that we can have more arrows, and we also know that it needs to start from a particular origin. So if we're looking at it in a particular coordinate system, say, again, our typical x and y coordinate system, then the arrow needs to start at the origin and it goes in points towards a particular direction. Now, what if we had two vectors? What if we had another vector right here, say vector u? We can add these two vectors together. You can use, visually, you can tend to think of it geometrically as doing something like tail and type of method, which you just move this here, and you draw basically the resulting vector, which will be the sum vector of the two. But analytically speaking, what you're doing when you're adding two vectors together is you're adding their different components together. So, for example, if these were both three-dimensional vectors, so if they were, for example, a vector v was a vector that contains vx, vy, and vz, and the same thing for vector u, which contains ux, uy, and uz. If I want to add these two vectors together, then I would have the resulting vector would just have, for each of its three components in this first column, it would just have basically the sum of these two things. Or if you want to say it in more linear algebra terms, it will be in essence the linear combination of this vector. So you would have v plus u equals then This would in essence be your resulting factor that came by adding these two factors together. Basically, you just add their components. Another way of writing this vector sum is, instead of doing it like in this typical vector notation method, you can also write it as the following. So v plus w is equal to. So another way in which you can note v plus w, these two vectors, is by, of course, what is here is in essence each of the elements we saw in the first row of, well, in the only row of v plus w. The only thing is we've written it in this horizontal fashion, and we can do this because in essence, what we have right here is the magnitude, or the components basically added together, times something which is known as a base vector of a given coordinate system. So this base vector basically tells us what are the basic units which we will have for our coordinate system. Say, for example, if it's a Cartesian coordinate system that is in 3 dimensions, we can extend this to z. These 3 little vectors are what we call the base vectors. You can see that they lie specifically on you can say, the reference of which you're using for your coordinate system. And this x hat, y hat, and z hat, in essence, they are vectors with a magnitude of 1. So they basically have a size of 1 unit, given what you want to use. And the basic idea of having these things is that from these base vectors, you can span the entirety of our tree, which is in this case the vector space, which contains all of the vectors in the 3D Cartesian coordinate system. That's why we can typically denote the sum of any two vectors in the 3D Cartesian coordinate system as v plus w is equal to their components added together times by their corresponding base unit vectors, basically. Another aspect which we can introduce now when talking about vectors is something called the dot product, which might seem a little bit abstract, but say for example you have again vector w and vector u, and they have a particular angle. So there's a particular angle between these two vectors, and of course they both start at the origin. Then I can say that the dot product, also called the inner product, is equal to the magnitude of the vector v. So its magnitude times the magnitude of the vector u times the cosine of the angle between the two vectors. So times cosine angle theta. This is a formulation for something that is known as the dot product of these two vectors. And in essence, the way in which you can think of it is you're finding this particular type of product from vectors gives you a scalar instead of a vector. So it gives you a number that is in R1 vector space, basically. So instead of R3, you get something that is just in R1, and a scalar, which is essentially just a number, any real number, or complex. But another way in which you can write the dot product is also, say if v and u are in R3, so of Cartesian 3D coordinate system, then I know that they have the components vx, vy, and vz, and this is times ux, uy, and uz. Then I know then that the inner slash dot product of this of these two vectors will be vx times the x component of u plus vy times the y component of u plus vz times the x component, z component of u. So in essence, these are two ways in which we can write the same thing, in essence, this being the dot product of vectors, but we can either write it in terms of the angle between the two vectors and their magnitudes, or we can write it in terms of you could say, the product of their corresponding components multiplied by each other, both of which give scalars. So in essence, what you get is in essence the same thing. Now, very interestingly, if we wanted to find the size of one of these vectors, say vector u, if we wanted to find its magnitude, then in essence, the magnitude would just be the square root of the dot product of u with itself. So in essence, it would just be u dot u and its square root. Now we can say that this is okay u squared, but to make this a little bit more clearer, say that we write this u dot u fully out. So what is within the square root if we were to express that fully? What we would then get if we use the second way of noting the dot product, so that it's the component times itself and the sum of that, it would be then ux times ux plus y times uy plus uz times uz. What you would have here in principle is, and the square root of this, of course, what you would have here in principle is ux squared plus uy squared plus uz squared. This is, if you can notice it already, this is basically the Pythagorean theorem extended, of course, to 3 dimensions because you have a z component. So, in essence, using the components basically that you have for your vector u, so your ux, your uy, and your uz, you can basically find the magnitude of this vector, so you can know how big it is, basically. Which is quite neat and fascinating and an interesting way to think about the magnitude of the vector. Now that we have all of this down, we can actually start introducing some index notation into this to make life a little bit more tricky, it might seem at least, but it will be useful for the further maths that we're going to be using. So the first thing that we're going to note is we had, for example, v equals vx, vy, and vz. We can write this these components of the vectors in terms of index notation. So then we would write vx as the following: v1, we would write vy as the following: v2, and we will write vz in terms of v3. Doesn't matter actually which one of these x, y, z you use, but as long as you stay consistent with your math and your notation, you're good to go. But typically, it is mostly denoted as vx being v1, vy being v2, vz being v3. We can do something similar actually for the base vectors that we have right here, for the Cartesian coordinate system that we're using to describe this vector v and vector u in our examples. And that being that our x hat, so the base unit vectors for this coordinate system, would then be noted as e1 hat, y hat would be denoted as e2 hat, and c hat would be denoted as e3 hat. This might seem like a very weird notation, but it pops up again and again a lot in physics. And this e1, e2, and e3, it stands for the word ein in German, which is just one. And it's like, from what I gathered, it's like a funny analogy to saying like, oh, you have all of these ones which make up a vector space, basically. So with that out of the way, so with knowing about the dot product, knowing about the addition of two vectors, and knowing about this new index notation that we use for the vectors and the index, or the basic vectors, we can now write, for example, any given vector in a Cartesian coordinate system, or actually in any coordinate system, using index notation. So instead of vx and vx times x hat plus vy times y hat plus vz times z hat, we can write v1 times e1 hat plus v2 times e2 hat plus v3 times e3 hat. Remembering again that these do not stand for power, so factor to the power of something, but they stand for index notation. So it's really important again to remember that. We can very clearly see that this vector v is a sum of a vector with a given index I times a base unit vector with a given index I, and we see that I starts at 1 and it goes up to 3, basically. This would be a very clever way of noting our vector, basically. It's another way of writing it. And if you take a look at this and you remember the Einstein summation way, you can just say that, oh, I can drop this, the sum sign, and just say that, oh, vector v is equal to vi ei hat, basically. As long as you just have these two indices, then you're good to go. Then you are indicating indeed that we're talking about a sum here and not something else. There are various examples of which we can use this notation and use dummy indices to make our notations a little bit more compact. Say, for example, I was describing the position vector of something in space. So in physics, typically, you would use a position vector r to describe the x, y, and z components of a vector. And I can write that as simply xi times e sub I hat. With xi, of course, being the corresponding components you have of this particular vector. So you have x1, x2, x3. If you remember the index notation which we used for Cartesian coordinate system, and we just wrote it very compactly in this form, which is a very handy tool to use. We can say that the sum of two vectors, say v and u, it would be equal to vi e I hat plus u I e I hat. And this, of course, because we need to add the components and sum that thing up, we can note this as vi plus ui times ei hat, which is a very nice way to note that this is the sum of these two vectors. Now, and interestingly, now this is where the index notation comes into play. We can write the index of u as a different letter or a different symbol. It is no problem at all because it still implies in essence, the same quantity right here, which is v plus u. If we were to write this in terms of vi and uj, then if we were to expand that, what it would look like is that v plus u would equal to vi e hat plus uj ej hat. And if we separated that, then we would have vi plus uj is equal to ei hat. And the reason why we can still separate or say put these components together and have this base vector here is because in this case, the ei and the ej are exactly the same. If you need further convincing, try to remember that this I stands for, this is in fact a summation of both U and V. So, in essence, with both of these, the degrees of freedom which you have are 3. They can only move amongst the x, y, and z axis. This index notation, again, it might seem a little bit confusing, and we're going to do more of it in order to come a little bit more in terms with it. But the simple fact that we know that, say, for example, v as vi ei hat, the simple fact that these two indices appear exactly 2 times and indicating a summation is the reason why we call these indices something known as a dummy index. And the fact that, for example, when you saw the sum of two vectors, that we could just easily switch from I to j if we wanted to, like we can just change the index notation as we calculate along. This is the reason why they call it the dummy index. And there is another type of index called the free index, which we will be looking at very, very shortly. Now, what about if we wanted to do the dot product of two vectors? How would we do that in index notation? So we have v dot u. Then in essence, you would think that, oh, this would just be then v e I hat dot u e I hat, right? This seems correct, but that is not exactly the case. And the reason for that being not the case is the fact that this, in general, is one term of the equation and not two separate terms as we had it when we were talking about v plus u. This is one whole term, and in one whole term, we cannot have these simply implying the sum of the components. So in this case, the sum of the v components and the sum of the u components of the vector u. Because it's one term, this appears 4 times, and it only has to appear 2 times in order to indicate that it is a summation. So hence why this expression using the same index for v as for u, it is not handy. So we need to actually change the index in order to imply that, that this is, well, a different summation, you could say, in these two terms, because this whole thing forms one term. So in this case, it is necessary that we write v dot u, that we change basically the dummy index. So it is necessary that we write it as v I e sub I hat, sorry, still a bit caught up on the summation, dot u j e j hat. It is actually crucial here that we change the dummy indices in this one term expression. Now, how you can go about doing this is, if you think about the fact that the dot product, we were able to rotate in terms of vx times v times ux plus vy times uy, and do that on and on and on, and essence find the linear combination of things. Then you can do the same thing with this. We can see that I can be 1, 2, or 3, and j can also be 1, 2, or 3. The only thing that we need to take into account right now is when multiplying the corresponding components to each other. So say, for example, vx times ux, we also need to multiply this by its corresponding basis vector, which would be E1 for Vx dot E1 for Ux. And the reason why we do this, even though we know that at the end of this equal sign we're supposed to get a scalar, is because in essence it doesn't matter that we noted it in this way, because the dot product of the two basis vectors would still be a scalar. So we would still, at the end of the day, no matter how many terms we have right here, we'd still get a scalar property, which is exactly what we noted that the dot product is. It should give a scalar property. So if you look at this, what you would get, and we will use the index notation for this to make things, again, consistent. So we have V1 and U1. What you would get right here, in essence, is just V1 and U1. And I can imagine you can think of why this might be. The two base vectors are both, in essence, because these two vectors are in Cartesian coordinate system, they're the same, you could say. So they're pointing in the same direction. And if they're pointing in the same direction, if you remember the first way in which we thought about dot products, so that was, for example, if I have E1 hat dot E1 hat, that is in essence the same as the magnitude of this E1 hat times the magnitude of the other E1 hat, and we know that their magnitude is 1 times the cosine of the angle 0 degrees. Cosine of 0, that's just 1, and we know that the magnitudes of both these vectors are 1, so 1 times 1 is just 1, so we know that this term is just 1 right here. So I will erase this. For this reason, we know that this will just be the same as V1, U1. But I mentioned that we want the linear combinations of all of the other possibilities. So for example, there is also the possibility of having V1 times U2, for example. I know that that isn't what I defined at first, and you will see why it isn't the case that this pops up in the definition of the dot product. If we have this, then we have to multiply by E1 hat, E dot E2 hat. And this will not be 1. in essence, this will be zero because even though these two factors are of similar magnitudes, because they are orthogonal to each other and they're 90 degrees basically, the cosine of 90 degrees is zero. So in essence, you will be multiplying 1 times 0. So it falls out, it becomes zero. And hence why this term falls out. And we can just remove that from the expression. I will not do this for every one of the terms because it's quite long like expression. But what you will see at the end is that the only terms that stay here is the ones where the numbers are in essence similar, where I and j are the same. So v2, u2, in essence, the expression that we have then for v dot u is this expression using index notation and using the dot product of the base factors because everything else falls out. If I have e2 dot e3, same problem would apply as e1 dot e2, and that is that because they are orthogonal to each other, the dot product is going to be zero, so that term just falls out, and hence why we express the dot product as being this particular combination. So if you notice something, every one of the term, I'm going to write at least one of them right here. So v1 u1 e1 hat dot e1 hat. Every one of the term had their corresponding indices right here. So for example, v1 for vx and e1 hat for x hat, and same here for ux and its corresponding basis factor, which is also x hat. The way in which you can use index contraction to note this is by writing this, of course, as simply vi uj ei hat dot ej. This is another way in which we can note the dot product, and it shows a very interesting property that is going to be used quite a lot, and that is the fact that we had ei hat dot ej hat right here. So this very interesting property, because it is quite useful actually for mathematicians, they found a symbol, or they found a way to compactify this on its own, and it's something called the Kronecker delta. So ij. The simple weird notation, the del here, Greek letter del, ij, this just denotes in essence the same thing which we wrote here. It denotes the e sub I dot the e sub j basically. But it's a notation which we use to write this shorthandedly called the Kronecker delta. So if we were to rewrite this again, we would have vi multiplied by uj, so the components at least, and remember that this indicates a sum times the Kronecker delta ij. And the Kronecker delta, you could say, serves as a sort of bookkeeping material. The Kronecker delta, so the ij, which we remember was the ei hat dot ej hat. It tells us when one of the components in our component sum, so v1 u1, v2 u2, etc., when one of those falls out, because this can be either 1, the magnitude, so the Kronecker delta, or 0. And you can remember why. When it was 1, it is when the I and j are equal. So when the I and j are equal, with base factors are in essence the same factor, so it's e1 dot e1 hat, then we have a value of 1. And it's 0 when these two base factors were not the same. So say if it's like the dot product of x hat and z hat, for example, they're orthogonal to each other, so the dot product of those two base factors is going to give a 0 value. So this is in essence this new term which we introduced right here, which is the Kronecker delta. A short interlude I'm doing right now at home is something that I forgot to do in the actual video, and that is if, for example, I have a Kronecker delta ij. An interesting property of this Kronecker delta is given any object, say vi, I can use this Kronecker delta to lower its index. This will be called the lowering of an index, and that will in essence give me the same object, but right now with a lower index. And basically what the Kronecker delta does is it transforms the I to a j, basically. There is a precise reason why it does this, and we will see why that is. And a similar thing can happen with a lower index being raised and made into an upper index. So for example, say I have now an object uj. If I multiply by a Kronecker delta with upper index this time of ij. What this does basically, it takes the j index of this u element and it transforms it into an I basically, and it raises it and making it an upper index into ui. Basically, this is called the lowering of an index and this is called the raising of an index, and you do that by using the Kronecker delta. Actually, before that, for example, if we want to raise the index of a vector u, say vector u with an upper index of I, if we want to lower its index, we can multiply it then by ij, this Kronecker delta, and that will give us u with a lower index of j. Now, we basically, in this thing, we can see that we inserted a vector and got a vector out of it. From this statement alone, we can see that, okay, I have to multiply the vector by something, which in turn gives me, in essence, the same vector, because if I and j are not equal for the Kronecker delta, then this would be 0, and this result won't be valuable. In order for this answer to be true, then I know that I and j need to actually, in principle, be equal. So what I know about this is that this Kronecker delta right here, it can be expressed as something at which if I multiply a vector or even a matrix by, then I will in essence get the same matrix out of it. And this in linear algebra is something that we know to be the identity matrix. Say for example, I had a square matrix of 2 by 2. It would look, for example, I'm going to call it C. I'm going to say that this column matrix C has the following numbers within it. It has the numbers, well, in the first column, it has the numbers 3 and 4, and the second column, it has the numbers 3 and 6. There needs to be something I can multiply this by, which gives me the same matrix at the end. Since this is in essence what is happening here, but with a column matrix. The identity matrix would in essence look like this. It would look like the following. Because if we take either a left or a right multiple of the matrix, it doesn't actually matter in this case. If we do that for the corresponding matrix C, so let's do at first the left multiplication of this. What we will get is actually, if we do matrix multiplication again, we do this times this, we would have that the first element right here would be 3 plus 0, it would just be 3. In the second row, basically, the first element you would have is actually, well, 0 times 3 is 0, and 1 times 4 is 4, so we would just have 4 right here. And if we do that again, but for this column, then we would have 3 plus 0, that is just 3. And then 0 plus 6, that's just 6. So basically, taking this multiple right here of this matrix C, just spit it out the same matrix C. And this is a very interesting property of identity matrices. And if you don't know much about them, I highly suggest you look a little bit into identity matrices, diagonalization, and things like that, which would be quite fruitful and useful. Knowing that you need something that in essence takes a matrix and spits out the same matrix, we know that a Kronecker delta in essence has to be an identity matrix that looks something, I would say something like the following. If we were talking about, for example, 3D Cartesian coordinate system, then it would be a 3 by 3 square matrix. So it will look like this. So this is how we know that we can express with, of course, the rows being, for example, I, and the columns being, for example, J. This is how we know that, for example, we can express the Kronecker delta in terms of matrices as well. And we can even swap the I's and J's. So, for example, if we were to, say, take a transpose of this, so we were to take a transpose of this matrix. Basically, if we need to take the transpose, we need to interchange the columns with rows. So for example, column 1 will be row 1. So I know if column 1 is to be row 1, that will be 1, 0, 0. So this column right here, you can imagine that we flipped that, rotated that. Now column 2 will be row 2. So if we take this, flip this, then we would have that it will be 0, 1, 0. And column 3 will be row 3. So if we take this, flip it, we would have that it would be 0, 0, 1. With, of course, in this case, because we made the columns the rows, this time this represents the J's, and this would represent the I's. But in essence, you can see right here that it is the same thing as before. So whether we may have it, the columns being I or the columns being J, or the rows being I or the rows being J, it is in essence the same thing. And this is a sort of a symmetry property of the Kronecker delta. So this is a very nice way to neatly introduce matrices while talking about this different, very tricky index notation type of thing. And it might seem very comfortable to just stick with using matrices instead of dealing with a lot of these complicated index notations. But the index notations will be quite useful. And the main purpose of introducing things in terms of matrices would be to make life a little bit simpler in terms of calculations, hence why we will be dealing more with them and even with determinants later on. So in this second interlude, we wanted to look at another form of the Kronecker delta, and that is basically a form of Kronecker delta that, say, if I have an object with an upper index of I, it's gonna give me the same object with, again, another upper index, but say with an upper index of J. So basically we're looking and we want to find a Kronecker delta that just changes the sign of the index without changing its position. So either whether it's an upper or lower index. We have such an object, and such an object is something which we will call hybrid Kronecker delta, at least in part 1 and at least in part 2 and part 3 of these videos, before calling it the Kronecker tensor, basically. But basically what this in essence does is it just changes the index from an I, as you can see right here, to a J. Now if this was a lower index changing mechanism, then what would happen here, say if we wanted to change UJ to UI with still a lower index, then we will denote this sort of hybrid Kronecker delta as the following, where the index which it has at the beginning is noted, well, diagonally opposite side on the hybrid Kronecker delta, and the one which it changes to is denoted on the lower side. So it changes from J to I right here. Now, what this looks like, say, let's look at this one hybrid Kronecker delta right here. If we were to express this fully, what this looks like in essence is the following. It looks like 1 Kronecker delta JK multiplied by another Kronecker delta KI. This might seem like a rather weird notation, and why have we introduced another index right here? Well, we can firstly see that these two indices right here are dummy indices, and these dummy indices imply summation, so that is a very crucial reason as to why they're here. And another thing that we can notice right here is we have these so-called free indices, which we will talk very much more about, especially in part 3. But these free indices in essence appear only once, in contrast to dummy indices. So dummy indices appear like at least 2, especially 2 times, and they apply summation. Free indices appear only once. And another fact of free indices is that they have to appear at least one time on the other sides of the equation as well. So if, for example, we have it right here, j and I appearing at least once in the term right here and only once, then they have to appear at least once on the other side as well, hence why ji. If we apply this contraction of vi with this hybrid canonical delta, and if we wanted to do it step by step, we can see why this in essence worked and why it delivers for you with upper index of j. Vi multiplied by this hybrid canonical delta k and I, as this ki here, you have I right here and you have I right here, so I can apply this contraction. And what this simply does is it just lowers the index of v and changes it from I to k, so we would have v k right here. This is the first basically index contraction that we did, and now we have to take this and contract it with this other canonical delta jk. So now we have to take vk, v with lower index k, and contract it with this canonical delta with upper indices of j and k. Now we can see that we have this these dummy indices right here of k, k, and we have one free index of j. So in essence, when we look at the equal sign, we have to have at least j appearing at least once on the other side of the equation as well, due to the fact that what we've mentioned before. So that would give us basically v with upper index of j. And you could just think of it simply in terms of if we apply this canonical delta multiplication, it just takes this lower index, raises it, and transforms it into j. Hence why basically, if you look at this in total, you put in vi, multiply it by the hybrid canonical delta, which basically has these two in the contracted canonical deltas, and it will give you v upper index j, which just basically shows you how it simply changes the sign and does nothing else. You can try for yourself and see how that similar principle applies to this one right here. Well, before we end the video of today's part on the journey to relativity, I want to briefly talk about index notation as it pertains to some things related to multivariable calculus, and more specifically, some very specific things that we can do with functions, known as, for example, taking the gradient of a function and also finding the divergence of a function. Now, that sounds like a little bit of jargon, though if you had multivariable, you already know what this implies. But the gradient of a function is simply, say if you have a three-dimensional function, say in 3D Cartesian coordinate system right here, x3, or say if we have a function that is a 3D parabola, or rather a cone, in a three-dimensional Cartesian coordinate system. Well, if we have our little cone right here, and if we take like a plane and slice exactly through this cone, then in essence, if we look at one of these points on this cone, we're going to zoom in a little bit now, we can see that this function is changing in actually both the y, in both the x direction. So there's a change. We are looking specifically at this point right now. There's a change happening in this direction right here, in the x direction. We will call this dx. There is a change happening in the y direction as well. We'll say it will be something like this. We'll call it dy. And there's a change happening in the z direction as well. So it would look something like this. Now, if we want to look at something that tells us, okay, how does this particular arbitrary function f, which gave us this cone, how does it in total, you could say on average, change with respect to these given three components? We can actually find that because these can almost very much likely seem like they can remind you even in essence of unit factors, though they're not unit factors, but they can remind you in some sense how you can from unit factors build any vectors given in, for example, 3D Cartesian coordinate systems. And similarly, we can say that, oh, this, for example, might be the resulting, like say, change of this function f. Now, the way in which we go by this more mathematically rigorously is by introducing the del operator, the del or nabla operator, in order to find the gradient of a function. The del operator simply looks like an upside down triangle, which looks like this. And what it stands for is basically the sum of partial derivatives of the given components that you have. For example, in Cartesian coordinate system, in 3D Cartesian coordinate system, the del operator would look something like this. It would give you basically a vector, which I should introduce the unit vectors right here. The del operator could in essence be thought of as a vector that each of its components, or each of its components, its elements in its column, are basically showing you how much a given function is changing with respect to a given variable. The del operator shows you, for example, how the function is changing. If it's a function in 3D Cartesian coordinate system, how the function changes here with respect to x, with respect to y, and with respect to z. Now, if we know this, then we can say that the so-called gradient of a function, which basically just tells you, you plug in a function in there, it tells you basically how does this particular function f change, and with respect to different components. So what you will get right here is the same thing as before, but you actually take the partial derivative of a given function, so f looks in essence something like this, basically. So basically the same elements you have in the column, but you actually calculate now with by putting in a function and find their partial derivatives with respect to the indicated component. So if we were to note this down, what it would look like is basically the same thing, but now with an f right here. In essence, it would be written as this. This would be the gradient of the function f. Now, before we use index notation to show how we can make this a little bit more compact and powerful, we need to make another necessary notation and abstraction. And that is, we will say that one of these partial derivatives, we will write it in terms of as well this component, or any of these components, del I is equal to the partial derivative with respect to f xi, where I, of course, in this case, could be I x1, x2, x3, and so forth. One thing that is concerning to us is that these things, they are vectors, because you can see that they're being multiplied by a given unit vector of x hat, y hat, and z hat. Even though earlier we decided to say that we can use, in terms of Cartesian coordinates, upper or lower indices for vectors. So this, in essence, would be the same as this. We mentioned that when it came to other non-Cartesian coordinate systems, that an upper index, a vector with an upper index is not necessarily the same as a vector with a lower index. And hence why when we're talking about vectors, when we mention things about the contravariant vector, we said that typically the contravariant vector, or rather the vector as we can generally call it, should be that upper index vector, basically. So for that reason, we want to have this del thingy having an upper index. And the way in which you can do that is basically by multiplying this by a Kronecker delta. So if we do the Kronecker delta multiplication, which I will write right here, I multiplied by a Kronecker delta ij, we should then get this del j with an upper index. And of course, this the reason why, by the way, I denoted the Kronecker delta right here is because now the order, for as a formality thing, now the sequence at which we multiply this does matter, because we cannot write it as the following. So Kronecker delta, because this indicates that we're taking actually the derivatives of the Kronecker delta. So in essence, it's like, oh, we're taking the derivatives right here. And that's not what we're doing. We're just multiplying this del operator right here with the Kronecker delta. So if we do that, then we can get this with an upper index. Now that we know this, we can actually use this compact notation to write something like the gradient of f. So the gradient of f, if we were to write it more compactly, we would say that the gradient would be, well, the sum of these components times f. So we would write it in essence as the Kronecker delta multiple of this component right here. This, of course, being in essence the sum of the different partial derivatives of f. So basically x, we can imagine this plus, well, this, etc., etc. So that goes on and on and on. And this EI hat basically indicates that you're multiplying this component right here by their corresponding base factors, basically. So you're multiplying this piece right here by x hat, this piece right here by y hat, this piece right here by z hat, etc., etc. And of course, the Kronecker delta of ij here is just to, at the end, to raise the index of this thing right here, so that you have it noted at the end of the day as a vector, since we know at the end of the day that this is a vector with elements in this column of this. So this particular first bit, second bit, and third bit right here. After multiplying the Kronecker delta by this component right here, what we're left with at the end is in essence the unit vector I times the same, almost the same thing right here, but now with the upper index on the del notation right here. And you can see immediately that because we have two I right here, we have our dummy index of I. So this immediately implies a summation. So you, in essence, have written this in terms of a very compact notation, and it's very powerful for other things which we can note in essence. Now, besides finding the gradient of a function, one other thing we can use this del operator for, which is pretty handy, is finding something known as the divergence of a vector. Now, the divergence of a vector, in essence, it is intuitively said something that tells you the strength of a vector field at a particular area. So say, for example, if we were to look at this particular region around the origin of our 3D Cartesian coordinate system, and we look at how many arrows were going out of this particular sphere that we're interested in, or this particular interval, we can see that if you have many arrows going out, then you would have a very, then our divergence would be quite high, and it will be a positive value. And the opposite would be true if a lot of arrows were going inward, because then you would have, in essence, a convergence instead of a divergence. And of course, the actual value of it would depend on the number of arrows you have going out in the case of divergence, which if you have a lot of arrows within this particular narrow region, you would have a higher number. So if this region was smaller, this would have a higher divergence than this other region. Now, for a better explanation, I would highly advise you check other videos on YouTube, such as those of 3 Blue 1 Brown on this topic, since they're very visual and very nice to get an intuitive grasp. But in order to, in essence, go immediately to what divergence actually means mathematically, it means, in essence, taking the dot product of a particular, of using the del operator, since you know already that this already represents a vector, with a given vector, say a given vector v. So in physics, you would write the arrow on top of this one as well, but in order to remain consistent with my notation, I will just write it as del dot v. This is in essence the divergence of this vector v. And what this looks like, if you remember having to write the dot or the inner product earlier, we denoted it as the components, say the x and the y and the z components, the product of those. So for example, it would be in this case the x component of the del, and the other components would be the following. In essence, this is telling you that you take the partial derivative of the component, say the x component, the y component, or the z component of your given vector. Of course, this is particularly useful because, for example, even though we noted vectors which we had constant coefficients, there are cases in which you can have a parameter for your given components. So in that case where you have a parameter, if you take the partial derivative with respect to, say, x, y, and z, you can very neatly basically find that property which we call the divergence of a vector. And of course, seeing that we used index notation to make life a little bit easier, we can note this as being the following, where this, of course, represents, if you recall, the del I, and this represents, well, our vector. So in other words, I can write it even more compactly as this. This is, in essence, basically our notations for the divergence of given a vector, say vector v. If you recall earlier, we mentioned that if you had the particular cross-section of your cone, a given three-dimensional multivariable function, then you can look at its derivative in the dx direction, in the dy direction, and in the dz direction. And what you find right here is a corresponding vector that would basically be the gradient of your say of your function in any given case. It turns out that if you have the gradient of a function, then you can find something known as the directional derivative, and that is in essence what this is supposed to represent. It represents basically the derivative of f, for example. So let me call it df. In general, in terms to a given direction, while the gradient was a vector which basically contained all of the partial derivative of the function f with respect to x, y, or z. If we take the gradient of f of a given function and find the dot product of it with the position vector, this position vector is, if I were to draw a particular point right here, point P, and it moves along a curve, the position vector would tell you how it changes with respect to the given curve right here. So if we were to do that, if we were to find the dot product of this, then in essence we would have what is called the directional derivative of the function. So if I were to make this a little bit more intuitively for you, if we were to write the vector full, so at the end of the day, if we were to find the dot product of the gradient of f with the displacement vector, then we would in essence have a multiple of the given component times the given component of the directional vector and the other given component, and we can compactly note this immediately in terms of index notation by saying that, okay, we would in essence have this. We would in essence have this as our directional derivative of a given function. To write this a little bit more compactly, we can note this as dxi multiplied by this. And this will be what we will in essence call our directional derivative in terms of index notation, and writing it well in terms of index contractions. One of the last things which we want to introduce in this video is the so-called Laplacian, which is in essence the dot product of the del operator with itself. And what this gives is it gives the following. So you have the del operator, but you have the dot products of it. So it gives you a scalar that consists out of whatever the partial derivatives of these components might be and the square of that. Using index notation and the notation of index contraction, you can of course write this more compactly. You can say that, oh, this might definitely be, for example, the del I, and because it has to do with summation, we know that these two have to be in essence the same, they have to be the same thing. So that is it for my part 2 on the journey to relativity. Right now, we're still not there yet with finishing chapter 1, as I tended to notice right now. It tends to take a little bit of time to explain, especially some of the things that had to do with index notations and such, but it's necessary as I noticed that it comes again and again afterwards. So we needed to lay this down, lay the foundations in order to go on further. Now, for the following video, we will do more things with matrices and especially introduce more notations. Looking forward to that, and I hope to see you guys there. Bye.